Hello everybody and welcome back to another video on my channel. Today we are going over another kinematics topic, this one being motion graphs. So without further ado, let's move on to the topic. Motion graphs involve motion, of course, but there are often three main types of motion graphs. XT or position time graphs, VT or velocity time graphs, or AT, acceleration versus time graphs. So let's go through each one step by step. The first type of graph, position versus time. In other words, an XT graph, where we have time on the x-axis, that always happens, and then we have position on the y-axis. So normally what happens is from these graphs, not only are we figuring out position, most of the time we're also figuring out velocity. But that's going to come in a bit. The next type of graph is a velocity versus time graph. So it's the same thing. It's pretty much the same structure, except you have velocity being on the y-axis and position being on the x-axis. So let me draw that really quick. Now that we have the velocity versus time graph up, what we can do now is we can move on to our final type of graph, which is the acceleration versus time graph. So over here we can draw acceleration versus time graph. Let me quickly finish drawing that. Over here I have the acceleration versus time graph, or A versus T graph. These are the three main types of graphs you'll encounter in kinematics. Of course, as we go on later, there's going to be force versus time graphs, energy versus time graphs, etc. But those are going to come much later in the mechanics section. So let's continue on how to read these graphs. So the first type of graph, position versus time, is relatively simple. So we're pretty much going to be reading position, velocity, and time. Now position and time is very simple. You just look at where the point is on the graph and you just figure out what the position is. But velocity is a little bit different. So let's say we have this graph over here, and this is how it is. Now the velocity is found out by determining the slope of that segment. So if I wanted to ask you, how would we find the velocity from within these two purple lines? We would take y2 and then subtract it by the initial position, and then we divide that by x2 minus x1, or the final time minus the initial time, or the time span. Now that's actually awfully similar and is the same thing as just figuring out velocity through the formula, but not all problems will give you numbers, and sometimes you have to read them off graphs. So for a position versus time graph, you'll be reading position, x, time, and velocity. Now for a velocity versus time graph, you'll be reading a few more things. Well, in reality, only one more. First, we have velocity and time, of course, which you can just figure out by reading the graph. But then, we also have acceleration and position. So let's draw a sample graph over here. Let's look over here. We created a simple velocity versus time graph, where we'll be able to read the velocity and the time just by looking at the points. But to read off something like acceleration, we would again have to look at the slope from the two specified points that are normally given in the problem, and where we'd have v2 minus v1 over t2 minus t1. So that's actually also the exact same formula we use for average acceleration. Now, where it gets interesting is when we have to find position. So if we have to find position between two specified time intervals, we look at the curve or the graph, whatever it is, and then we calculate the area under that between the x-axis and that curve. So if we wanted to figure out the position between the second and third pink dashes, we'd have to figure out the area of the shape shaded in pink over here. So basically we'd have to be figuring out the area, and sometimes it's very easy, most of the time it's very easy, but in calculus sometimes it does require integrals, but we won't be focusing on calculus-based physics in this series, just algebra. In total, this can pretty much find out the most things out of any of these. This can find out everything from time to acceleration. So this can figure out time, position, velocity, and acceleration just from looking from this one graph. Now the next thing, or the third and final type of graph we have over here, is going to be the acceleration graph. So let me quickly draw that. Here we have the acceleration graph, and it's pretty simple to understand. Now, of course, we can figure out acceleration and time just by looking at the points on the graph, but if we wanted to figure out velocity, there's nothing beyond acceleration, we'd have to find out the area. So if we wanted to figure out the average velocity between these two dashed lines over here, we'd have to figure out the area under this curve, or just the area of this rectangle shaded in pink over here. So it can't figure out as many things as the velocity graph, but it can figure out time, velocity, and acceleration, just not position. Enough with demonstrating how the graphs work. Let me pull up a quick example and let's solve it. I drafted up a quick problem over here, and this has 3 parts. Number 1, what is the velocity at t is equal to 4? Number 2, or number B, or part B, what is the acceleration from t is equal to 5 to t is equal to 7? And last but not least, what is the displacement from t is equal to 0 to t is equal to 2? And when I was explaining it earlier, I actually said position, but it's displacement. So my apologies. What we have to do is, the first thing that we have to do is figure out what the velocity is at t is equal to 4. Now t is equal to 4 is this point over here, and reading the graph, it shows that the velocity at t is equal to 4 is equal to 10 meters per second. For part B, I'll also put it over here. What is the acceleration from t is equal to 5, t is equal to 7? What we have is we're starting at 25 and ending at 15 meters per second for velocity, and we're starting at 5 seconds and we're ending at 7 seconds. So v2 minus v1, so that's 15 minus 25, or we can write the formula first. v2 minus v1 divided by t2 minus t1, but then this becomes 25 minus 15 over 7 minus 5, 15 minus 25, not 25 minus 15. Then what happens after that is it becomes negative 10 divided by 2, or it becomes equal to negative 5 meters per second. So the answer to this, the second part, is negative 5 meters per second. Now the third and final part is what is the displacement from t is equal to 0 to t is equal to 2. So basically, what we have to figure out is the shaded area that I'm showing below. So, as you can see here, it is a right triangle, since if we draw a line straight down from t is equal to 2, wherever the velocity is at, and we have the horizontal line, we get a right triangle with sides 2 and 10. Now the area of a right triangle is 1/2 times the base times the height. So that's equal to 1/2 multiplied by 10 multiplied by 2, and that is equal to 10. So the displacement is 10 meters. So that's pretty much about it for our examples today. I'm probably going to continue this in my next video because there are a large variety of problems. So I might create a short video in the near future with 2 or 3 more examples. So thank you so much. See you in the next one, and bye-bye.